All right, everyone, integrals 1, day number 3. Some more methods for integration coming your way. And a little bonus one that might be attached to the partial fractions method. So we got to know how to get common denominators as well as divide using long division. So let's get it started. All right, so real quick, when we're dealing with partial fraction method or long division, we're dealing with rational functions. Specifically, in the case of our course, with polynomials in the numerator and denominator for these rational functions. So that's a first indicator that you're going to either be dealing potentially with partial fractions or long division. That is, of course, given that our previous methods of traditional u substitution and change the variable do not work. So let's talk about the different forms. Partial fraction decomposition method typically comes in this form, okay, where we'll have some kind of either linear or constant here in the numerator and some factorable quadratic in the denominator. Now, partial fraction decomposition can be done in other ways, but this is the typical way you'll see in this course. Now, the denominator will be factorable, and the numerator will be some value other than 0. So it could be 2x plus 1, it could be 1, it could be 3x, it could be any combination of those. The two steps in integrating using partial fractions are to decompose, which I'll show you how to do here in a minute, and then integrate using other methods that we have available. It might require u sub from there, or potentially change the variable. This is just a method to get us toward an integrable or integratable. I don't know the language for that because I'm not an English teacher, but that might not be a word. But it gets us to where we want to go. Whereas long division typically comes in the form of some polynomial over another, where the degree of the numerator, right, in this case n, is greater than or equal to the degree of the denominator. So we're going to divide and then integrate. Now, of course, if you can use a u sub, skip both of these methods, right, or any sort of traditional methods, because these are not the most efficient. They work. They're just how shall I say, sledgehammer for the job potentially of a ball peen hammer. So anyways, let's look at an example of integration by partial fraction decomposition. Okay, so this meets the requirements or the criteria for partial fraction, where the denominator is factorable and the power of the numerator is less than that of the denominator. So I've got a linear function over a quadratic where the quadratic is factorable. So let's get to it. First thing you want to do is you want to factor the denominator. So I've got x minus 1 over x times x plus 1. All right, now my goal is to put this expression, this integral, into the form a over x plus b over x plus 1. All right, where a and b in this case will be numbers, right, real numbers. So how could I do that? Let's work with the decomposition portion of this. So x minus 1 over x, x plus 1, we want to equal a over x plus b over x plus 1. The reason why I want to do that is because I see a whole lot of natural log going on in this integral over here. All right, so I'm going to multiply both sides by x, x plus 1. Okay, so let's do that. As you can see on the left side, as I multiply by x times x plus 1, the numerator survives that operation. Everything else is cleared out. On the right side, I'm going to get a times x plus 1 and b times x. All right, so what I want to do is I want to solve for x here. Actually, I don't want to solve for x. I want to solve for a and b, but I can do so by finding values that will make this simpler. So if x equaled negative 1, the first term, a times x minus 1, would disappear. So the left side would be negative 1 minus 1, which is negative 2. Ax plus 1 would disappear, and I'd get b times negative 1. So this would be true when b equals a half. Okay, what about when x equals 0? Well, when x equals 0, b times x disappears. So 0 minus 1 is negative 1, and a times 0 plus 1 is 1. So I get a equals negative 1. All right, so I've got b equals 1/2 and a equals negative 1. Therefore, what I can say is that this expression within the integral would be equal to the integral of a over x, which is negative 1 over x. And I'm going to split this into two separate integrals, plus the integral of b over x plus 1. Now I'm going to pull the 1/2 for b out. That'll leave 1 over x plus 1. Now both of these can be integrated very easily. The first will be negative natural log of x. The second will be 1/2 natural log of x plus 1. This is an acceptable form. I could also compress it. If I brought the 1/2 in, that would be natural log of the square root of x plus 1. So let's rewrite that. Natural log of the square root of x plus 1 minus the natural log of x plus c. And I can combine these using the subtraction rule with logarithms. When you're subtracting two logs, you can combine them using division. So again, any one of these three would be acceptable forms, but that would be our integral. Okay, awesome. Let's look at another example. Okay, let's take this first of all and factor the denominator. So I'm going to have an x plus 1 and an x minus 1. What I want to do is get this integral into the form a over x plus 1 plus b over x minus 1. All right, so I'm going to get it into that form, but I got to decompose it in order to do so. So 2x minus 3 over x plus 1, x minus 1. As you get good at this, you're going to start skipping steps and just working right to what you're looking for, which is fine as long as you show sufficient mathematical understanding along the way. Okay, so I would be okay in this point of saying that 2x minus 3 would be equal to a times the quantity x minus 1. I'm just multiplying both sides by the denominator of the left side. And I'll see that there's some reduction. Now the two values I would pick would be x equals positive 1, which would rid us of the first term with ax minus 1. So if x is positive 1, I'd get 2 times 1 minus 3, which is negative 1, which would equal b times 2. So it looks like b would equal negative 1/2. Okay, if x equals a negative 1, then I'd get 2 times the negative 1, which is negative 2, minus 3, which is negative 5, equal to a times a negative 2. Okay, so it looks like a equals 2/5. All right, so now I can work with that. So the integral of 2x minus 3 over x squared minus 1 dx is equal to a over x plus 1. So I'm going to work and pull that 2/5 out and leave a 1 inside, plus b over x minus 1. I'm going to pull that negative 1/2 out, as I've been doing so far. Leave this as that. Okay, now each of these would technically require a u sub, okay? But once you get used to this process and you start recognizing this, you're going to clearly see that this would be 2/5 natural log of x plus 1 minus 1/2 natural log of x minus 1 plus c. Okay, these cannot be combined at this point unless I do something with the coefficients out in front. I could bring them in as powers. I'm actually just going to leave it right like this and call that good. That is the integral of 2x minus 3 over x squared minus 1. Okay, so let's look at an example which might fool you into thinking you should use partial fraction decomposition. But there's actually a really good, clue going on here. I cannot factor the denominator. Now, this bonus method is actually called the completing the square method. Okay, so I'm going to use the method of completing the square, or actually, well, you'll see in a second here, in order to do this. So I can't factor the denominator, but I can write it in a form that at least part of it can be factored. Okay, so the portion here in the parentheses I can factor, right? And in this situation, this is very nice because I can write this as the quantity x plus 1 quantity squared. Okay, so maybe as you look at this, you see, wow, that kind of looks like arctangent, and you're right. Okay, if I set u equal to x plus 1, all right, then du is equal to dx. So I can do a substitution, allowing this to take on the form which would give us the arctangent of u plus c. Of course, that's in terms of u. We have to go one step further, and u equals x plus 1, and we've got an answer. That's one example of where the completing the square method, which rarely comes up, but on occasion will, might fool you into thinking you can use partial fractions, but I'd go that direction with it. All right, let's do some long division. All right, before we do any long division, we got to remember how to divide. So let's go ahead and look at how to do that. So of course, if I want to take 11 and divide it into 43,985, well, 11 goes into 4 0 times, but it goes into 43 3 times. So I'm going to then multiply 3 and 11, giving me 33, and I subtract. Okay, so I get 10. Now I drop down my next number, which would be 9, making that 109. So how many times does 11 go into 109? It goes in 9 times. Okay, so I multiply through. 9 times 11 is 99. I subtract. I get 10. I drop down my 8. I get 108. How many times does 11 go into 108? 9 times again. So 99. You start to see the pattern that we all learned in whatever grade that would have been. I don't even know. Okay, I subtract. I get 9. I drop down to 5. Looks like 11 goes into that 8 times, which is 88, which gives me a remainder of 7. So what the heck do I do with that? Okay, so what we do with that is that 43,985 divided by 11 is equal to 3,998 plus 7/11. We're going to use that process with polynomials now. So let's do that. All right, so just like 43,985 went inside the division symbol, we're going to put x plus 3 inside the division symbol. Okay, so 4x minus 1 is going to go outside. So how many times does 4x minus 1 go into x plus 3? Well, it goes in 1/4 of a time. Right? And the reason why is because I want to match up those initial terms. So 1/4 times 4x is x. And 1/4 times -1, I always use parentheses here, is -1/4. So as I subtract, the x's reduce, and 3 minus a -1/4 is going to be 12/4 minus a -1/4, which is 13/4. So the integral of x plus 3 over 4x minus 1 is equivalent to the integral of, 1/4 plus 13/4 over 4x minus 1. So I'm going to put 13/4 over 4x minus 1. You might be thinking, well, that doesn't look that much easier. And to some extent, you're right. I'm going to split it up into two integrals. Integral 1/4 dx plus the integral of 13/4 over 4x minus 1. Okay, so the first portion, relatively easy to see. That'll be x over 4. The second portion, we're going to use a u substitution. So let's work with u equal to 4x minus 1. So du would be equal to 4 dx. Well, I want this to equal 13/4 dx. All right, so I want this to equal 13/4 dx. So let's work our way around here. Let's divide by 4 And then I want this to be 13/4 dx. So I got to multiply both sides by 13/4. Okay, so the proper substitution here then would be 13/16 du is equal to 13/4 dx. That will rid me of any of the extra garbage there. Okay, so I'm going to write plus 13/16 du, right? That replaces 13/4 dx, and then I'd put 1 over u. Therefore, our integral, this is kind of a complex situation, but it worked out. 13/16 times the natural log of u, which was 4x minus 1, plus c. Okay, so using long division, I've got that as my answer. Okay, let's do one more example of long division, and then we'll call it a day. Let's move on down here. Okay, so in this example, the powers, how did I know I was using long division? Well, the power here is 1, the power here is 1. All right, so in example 5, notice how the power of the numerator is greater than that of the denominator. That's another indicator we're going to use long division. So let's divide. So that'll be x minus 2 divided into 3x squared minus 5. Now, whenever I have a missing term, I always at least put a placeholder in there so I don't mess up my algebra. So x goes into 3x squared how many times? Well, 3x times. Okay, so 3x times x is 3x squared minus 6x. So I distribute the 3x to x minus 2. I get the following. I subtract. The first terms cancel exactly how I want them to. So 0 minus a negative 6 is 6x. I drop the negative 5 down. How many times does x go into 6x? Well, it goes in 6 times. So I get 6x minus 12. I'm again going to subtract. And it looks like, oh my gosh, again, I get 7 as my remainder. Okay, so what we do from here is we're going to rewrite the integral. So the integral will be 3x plus 6 plus 7 over x minus 2. Okay, that's how we would rewrite that in a long division simplified form. Okay, so let's do these individually. You don't have to do this. I'm just doing it to reiterate some of the rules of integration and properties. I'm going to pull out the 7 integral of 1 over x minus 2 dx. Okay, these are really nice to work with. This will be 3x squared over 2 plus 6x plus 7 times the natural log of x minus 2 plus c. There you have it, guys. That's long division and partial fraction decomposition with a little treat there involving completing the square. So we'll see you in the next video. Have a great day.